Hey everyone, thank you so much for watching my YouTube channel. Maybe the first thing to quickly address is that I've renamed this YouTube channel from Henry AI Labs to Connor Shorten. Maybe if you've been following me on Twitter or LinkedIn or something like that, I've recently joined Semi Technologies full-time as a research scientist working on the Weaviate vector search engine. Maybe on Henry AI Labs, I've been making content about Weaviate for maybe 6 months or so, so it's not like a complete left turn in what I'm doing, but overall, this definitely in my life has represented a huge change, and I hope to still be kind of delivering useful content in the deep learning space through this YouTube channel, but I think it's better to rename it to Connor Shorten rather than Henry AI Labs. It's always just been me talking, but just further kind of brand the channel as sort of my commentary on different things I'm doing. I'm especially interested in building this Weaviate podcast. Please check it out if you haven't already. This Weaviate podcast is sort of my passion project with creating content right now. I've had some incredible interviews, and I think this kind of platform could be a really exciting way to generally push deep learning education. So back to the content of this video. This video is a podcast recap of my latest podcast with Etienne Dilocker on Approximate Nearest Neighbor benchmarks. So what you're looking at on this screen are the Weaviate ANN benchmarks. This is the web page that we're announcing that documents this kind of idea. So to give you the quick overview before getting into the slides and going through each of the podcast chapters, this has different metrics. So recall at 1, recall at 10, recall at 100. This is how accurate the approximate nearest neighbor search is going to be from the pure correctness standpoint. Then you have engineering things like the queries per second, the latency, P99 latency, and import time for building the vector indexes. And then you have hyperparameters on this HNSW approximate nearest neighbor search algorithm. So I'm sorry if I just overloaded you with information without the beginning. The beginning of this idea of approximate nearest neighbor search, ANN, is that you have these data structures like ANNOY or HNSW. Probably ANNOY is a great place to start, and it's kind of like a binary search tree, but you have these n-dimensional vectors. So instead of having a single node to split the data like a binary search, you instead have a hyperplane that cuts the space. So the hyperplane will cut the space, and that's how you make the comparison whether you how you traverse the tree. And now there's a little different thing with HNSW that I unfortunately can't tell you the whole detail of it yet. I'm at Weaviate and studying this thing, so eventually I'll give a really good explanation of HNSW, hopefully. But the difference between the tree structure is it uses some kind of graph structure with some kind of thing about small world networks. And small world networks, if you've seen things like network science, it's this extremely interesting phenomenon where, if you have social hops in a social graph, somehow you're connected to, say, Barack Obama and like 6 hops or some famous person through this kind of connectivity structure. And it's very interesting, and they further use this for these vector distance benchmarks. So that's a quick look at the algorithms. Let's get more into the actual ANN benchmark thing. So approximate nearest neighbor, the A stands for approximate. So what it is you're trading off that exact nearest neighbor calculation for speed and efficiency. So instead of you take your query and you put it into a vector space, and instead of doing the dot product with every vector in your collection of documents, say you have like a billion tweets or a million images, so on, instead of doing the dot product with every vector, you have this approximation that saves you a lot of that computation, but you trade off the accuracy. So when we say recall at 1, recall at 10, recall at 100, we're seeing how many return neighbors with the approximation algorithm it takes to get the exact nearest neighbor. So when they say ground truth in an ANN benchmark or an ANN dataset, the ground truth are the exact nearest neighbor. So that means somebody has done that exact dot product calculation to get the exact nearest neighbors, and then you're seeing how well the approximate algorithm like HNSW and then the different hyperparameters of HNSW, how that's going to impact the loss with the compression of doing this kind of space division to speed up the nearest neighbor search. So hopefully that's a good explanation of what ANN benchmarks are and what we're trying to document with these data sets. So now let's get into the data sets themselves. So there are 4 data sets presented on this webpage. You have SIFT 1 million, GLOVE 25, Deep Image 96, and GIST 960. So the way that I understand this, there are 3 key things to look at with these ANN benchmark data sets. So the first of which, that pops into our head, and then we'll talk about this as we're interviewing Etienne and going through the key lessons learned from Etienne, who's built this thing, is the size of the data set. So So say SIF 1 million, you have 1 million objects, glove 25, you see 1 million vectors. Each vector has 128 dimensions. Then as you look at glove 25, 1.18 million vectors, deep image 9.99 million vectors. So the first thing to note is that we don't have this linear scaling. The whole point of these ANN algorithms is that we have this kind of logarithmic scaling. I'm not sure if it's exactly logarithmic or how that works, but as you go from 100,000 to 1 million to 10 million vectors, the performance isn't going to decrease like crazy. That's the whole point of the algorithm. I mean, it's going to decrease, but it's not, again, it doesn't have that linear scaling. So going from 100 and so on, I'm sure people out there who watch this channel already have that idea of like time complexity, storage complexity, order log n, order n, and seeing that kind of scaling in real life, as Etienne describes, is a really nice thing to just observe in a real engineering system. And so that's pretty interesting. All right, so here's the second thing to be looking at is the dimension of the vectors. So we have 128 dimensional vectors, 25 dimensional vectors, 96 dimensional vectors, and 960 dimensional vectors. So why this matters is because that's how the dimensionality of the vector is going to be impactful when you're making those distance calculations. So as Etienne describes, this is probably the most impactful thing to look at when you're looking at these data sets and saying, how does this compare to my data set that I'm going to be using with a vector search engine? So then the last thing to consider, and this one is a bit tricky to kind of understand, is kind of the clustering properties of the vectors and sort of like distance histograms, sort of the general distribution of your vectors. So yeah, that's a tricky one to kind of reason about quickly, but here's an example of why you can't use random vectors as a benchmark that will hopefully explain that third point of clustering properties, looking at the averages of the distribution of distances to query points and getting that kind of sense of how that impacts something like this kind of search algorithm. So when you have random vectors that are, say, evenly spaced out, so there's no clustering in the vector space, these approximate nearest neighbor algorithms are not going to be useful for that because they exploit that clustering properties. Hopefully that was good. So when you put these things into vector representations, you run them through inference to deep learning models, they tend to cluster the data, and these ANN algorithms exploit that cluster structure to achieve this speed accuracy, to achieve the speed increase. So hopefully that was a decent explanation of that. So here's another thing that's very interesting about this benchmarks before getting into the podcast recap itself. Something you can tell from this set of tables is how varying these HNSW build parameters will impact performance and getting at like an exact sense of what might happen. So this chart is showing different values of EF construction, max connections, and EF. So you see this table going 64, 128, 512, 1632, 64, 128. These are the different parameters that you can use when you're setting up your HNSW in Weaviate. And you can kind of see like how that changes the queries per second that you achieve, the recall, the mean latency. So if you have your Weaviate instance and you're curious what turning these knobs might do, now you have like some numbers and some data sets that you can hopefully map your data set to one of these data sets, and you can look at these numbers to get a sense of how playing with these hyperparameters could impact the performance. So hopefully that's a useful description of this web page. I'd be more than happy to answer any questions or talk about any ideas you might have. So with that said, let's get into the chapters of the podcast. This video is a recap of Weaviate Podcast number 16, Approximate Nearest Neighbor Benchmarks with Etienne Dilocker. This is one of my favorite Weaviate podcasts because we get into the details of one of the core drivers of large-scale vector search. We want to encode our queries into vector representations and use this to find the nearest neighbor by doing vector distance calculations within a massive vectorized dataset. So we use these approximate nearest neighbor algorithms in order to divide up the space and achieve this kind of nearest neighbor computation in a reasonable amount of time. So this podcast documents the efforts of Weaviate to benchmark these approximate nearest neighbor algorithms like HNSW on different data sets that vary with respect to how many vectors we have, the size of each of these vectors, and then the clustering, the distributions of these vectors within each data set, and overall get a sense of the performance so you can understand exactly how well Weaviate may work for your use case. I learned so much from this podcast, and I really hope you enjoy this video as well as the podcast itself. So the opening topic of the podcast are ANN benchmarks in Weaviate, and I think going through the website just now was a good overview of sort of the details of it, hopefully clear enough. Again, happy to answer any questions. But let's kind of get into the thinking around creating a benchmark for your software. And Etienne has written a really excellent Twitter thread that summarizes these ideas that I'd like to read to you really quick. So Etienne writes, You may have seen that we just published Weaviate benchmarks, so now's the time to share some learnings from benchmarking your own software. Let's talk about goals, biases, transparency, and related benchmarks. So it's pretty interesting right there thinking about this idea of benchmarking your own software and producing metrics that say X is better, say like company X is better than Y and Z, and they all compete, they do the same thing, so they're all interested in having metrics that produces, say that this is the best system for this kind of thing. And it's interesting in, academic benchmarks, we have things like ImageNet, Glue, Squad, Wikitext for language modeling. We of course have these benchmarks that kind of document the state of question answering, language modeling, image classification. So yeah, it's interesting what Etienne writes about biases, transparency, how this relates to creating benchmarks for companies, especially this open source company space. I think generally this is an extremely interesting topic. So Etienne continues to write, like any good article, a benchmark should answer a specific question. This question may be, is X faster than Y? How fast is X? Or how does X scale? Whatever you pick, you should design everything around that question. You will most likely be in a situation where you have more measurements than you can present. Defining the central question makes it much easier to keep or discard the results you find. So we see these questions, we have queries per second, we're looking at the latency in this chart. So we're trying to ask these questions that the benchmark should answer related to system performance. Etienne continues, think twice whether you want to do a comparative benchmark. There is massive value in those, but can one vendor really be objective? I doubt it. You are bound to know your own system better than others. See skewed experience here. In our case, our strength is running Weaviate, not other solutions. The message we wanted to convey is, this is the performance you can expect when you run Weaviate in production. It may be faster than others or slower, but that's not the motivation behind the benchmark. So you see how what the table is showing you, how you can vary these HNSW configuration parameters. You saw EF, max connections. You can see how varying these parameters and building your Weaviate vector search instance, how that varies the performance of the system. So Etienne continues, the idea is that you have a specific performance requirement. When you're looking into Weaviate's performance, you have probably already decided that you like it for other reasons. Now the question is, can it match your requirements? We build open source software, so it comes naturally to us that we are open about benchmarks. The scripts are public, infra and config is clearly visible. Even if what you're benchmarking is closed source, I'd still go that route. Make it as easy to reproduce as possible. So these benchmark scripts, and I'm actually not super knowledgeable about this, so I'm not going to comment on it too much, but you see that the ANN benchmark scripts are included in a GitHub repository, and it seems easy enough for anyone to add their own data set if you want to keep building on this, which I think is really exciting. So that kind of idea, and very exciting, this idea of having this open source benchmarking, trying to make it as open as it can be. Etienne continues, this serves three goals. You can trust that our results are reliable. If you have a doubt, try it yourself. You can reuse the scripts to benchmark in your situation. We can rely on your help if we make a mistake. Contributions are welcome. What other benchmarks exist? Why did we not just add Weaviate to Eric Bernardson's ANN benchmarks? Now we're back at our original question. For us, it was about what to expect in production, while Eric's benchmark is built around the idea of embedded libraries. Now we have two choices. Either isolate Weaviate's ANN implementation, but then you can't draw conclusions about production latency and throughput, add Weaviate end-to-end, then it's not comparable to embedded solutions in the benchmark. That's why we decided against both. It goes without saying that I believe there is still a lot of benefit in a comparative benchmark for vector search engines where they are all run end-to-end, including network latency, object retrieval from disk, etc. That concludes part one, biases, transparency, objectives, and the ecosystem. And we haven't even talked about the technology challenges of benchmarking. That's for my next thread tomorrow. If you're curious about the Weaviate benchmarks mentioned above, check out the Weaviate ANN benchmarks page. So I really hope that you found that Twitter thread useful from Etienne. I think Etienne has just so much knowledge in the engineering side of these things, and it's always so interesting to be interviewing him on the Weaviate podcast. So that's probably enough on this general topic of ANN benchmarks and Weaviate. So the next question is, what makes each data set different? So I think there are three key things to look at: the number of vectors, the dimensionality of each vector, and then kind of the clustering properties of the data set. And that last one, again, tricky to quickly get a sense of how to really have a quick intuition abstraction that describes that last thing in my view. Maybe things like, say, histograms of distances, if you have bimodal distributions of distances to your query points, or things like that, kind of looking at the clustering properties of the data set. Anyways, so that's what makes each data set different in these approximate nearest neighbor benchmarks. So then you might be asking, how does this relate to my data set? So you look at things like how many vectors do I have? And again, you don't have that linear scaling, but then you look at how many dimensions are you using to embed your vectors. So Etienne describes that generally you're seeing 384 dimensions for text and about 1,024 dimensions for images. You see models like Clip that try to put these in the same embedding space, and maybe that's like 784 dimensions to do some number in the middle of that. But thinking about how many dimensions you're using to embed your vectors, and as Etienne describes, so do you really need all that dimensionality in your vector? That's an interesting question because say Barlow twins, the contrastive learning paper from Facebook, they showed continued improvement as they scaled up the size of the vectors, going from 4096, 8192 up to 16,536 dimensions in the vector representations of images. And they're showing that the performance is continuing to improve as they continue increasing the size of the vectors. So that's an important thing to consider, because if you cut the size of your vector dimension in half, you could be having huge engineering benefits from doing so. So that's kind of a thing to be thinking about as you're designing these kind of vector search systems. So then coming back, I think I already talked about this quickly, but what is the problem with random vector benchmarks? So say you generate random vectors, then you compute the exact nearest neighbors from the random vectors, and then you're benchmarking these algorithms with that. The problem is that random vectors don't have that clustering structure, so you're missing out on that kind of detail. So then let's talk about clustering. So clustering, I think, is extremely interesting in these kind of vector search systems. So there's a paper that is called Learning to Classify Without Labels. And so what they basically do is they use these self-supervised learning algorithms to form clusters in the spaces, and then you just kind of assign categorical labels to the clusters. So rather than labeling data with the one hot encoded symbolic labels and then you predict the label, you label it with the cluster assignment, sort of. And I think that's a pretty interesting idea. It's so it kind of lets you have this like open-ended label set, which is interesting. I don't know if that's quite like open set classification, that word, but again, you have this more open-ended flexible interface for assigning labels with the clustering interface, rather than kind of the supervised learning kind of setup. And then just generally you see this kind of phenomenon of clustering representations. Generally there's a lot to that. So then I was kind of talking to Etienne about some things that I'm very interested in. So I was asking him what he thinks about this idea of recommendation re-ranking on top of retrieval. So you have these multi-stage pipelines where say you have a coarse-grained retrieval and then you have a more fine-grained retrieval, and then maybe you append that downstream task. And particularly the task I'm interested in is recommendation, personalization. How do you tailor the search to individual users? So I'm curious about this idea of, it looks like a lot of ways to decompose the recommendation task. So do you make one recommendation at a time? Do you consider the structure of sequential recommendations? Do you have embeddings for the content itself, or is it maybe have some kind of license like movies where you can't actually use the content itself to produce the embedding, so you use some other heuristic like reviews of the movie to form the embedding of the movie itself? All these little things about recommendation is something I'm really interested in, as well as this re-ranking interface. And just generally, I'm trying to increase my understanding of how we can put re-ranking layers on top of the output of these vector search retrievals to tailor it to different applications. So then something that I think is really cool is Weaviate's class properties schema. And as we're talking about approximate nearest neighbor search and these index structures that get built, what you can do in Weaviate is, if you want to say have multimodal data or multilingual data, or even just these bipartite graphs in something like recommendation. So let's do the bipartite graph thing. So say you have users and then you have items. You could have 1 million users and have an HNSW graph for the users. You could have, say, 1 billion items and have an HNSW graph for the items. You just create these two classes in Weaviate, and then you just have this cross-reference, say user has click item or has review item, something like that. And you can build up these two HNSW structures. And I think it's a really great interface for, say, collaborative filtering, which I'll get into more later. So then I'm trying to increase my understanding of Weaviate. And so if you want to help me out with working on Weaviate, I'm very curious in trying to learn how to build Weaviate custom modules and increasing my education on Weaviate custom modules, the Weaviate core and the Python inference containers, and how we add, say, new Hugging Face tokenizers and models to existing modules. as well as how we would extend these modules to create custom modules. So Weaviate has some modules like question answering, named entity recognition that perform this functionality. And I'm trying to learn more about really how this works. And this is pushing my skill set to try to understand something like this, but I'm having a lot of fun doing it. And I think it's a very interesting system. So hopefully you enjoy this podcast with Etienne Dilocker. This was definitely one of my favorites, this approximate nearest neighbor search thing. I think it's one of the core drivers of these vector search engines, and I really hope you found this useful. And please leave me any comments or questions if you want my advice with something.